Here is a piece of bookkeeping that ought to take 10 seconds and does not. 2 electrons in a helium atom. Write down their wave function. You put the first electron in one orbital and the second electron in the other. And then you stop because you have just told a lie. You said first and second. Nature has no such thing. So you fix it. You write the same product again with the labels swapped, subtract one from the other, and the lie cancels. 2 electrons, 2 terms. Fine. Now do carbon. 6 electrons, 720 terms. Now do a small organic molecule, 20 electrons, and you are writing out 2.4 billion terms, every single one of which is saying exactly the same physical thing.
And every one of those terms exists to cancel a fiction you introduced yourself. That is the tell. When a notation forces you to write down an enormous amount of structure, whose only job is to undo something you should never have written, the notation is not inconvenient. It is wrong. And this is not a complaint about tidiness. It is a complaint about what the symbols are claiming. Every time you write electron number 7, you assert that there is a fact of the matter about which electron is which, and there is not. So you write the assertion, then spend factorially many terms taking it back.
Where does that determinant come from, historically? Because somebody must have noticed that the subtraction has a pattern.
John Slater, at Harvard, 1929, in the Physical Review, a paper called The Theory of Complex Spectra. Before him, people enforced this anti-symmetry with group theory, and it was so unpleasant that a generation of physicists nicknamed it the Gruppenpest, the group theory pest. Slater's move was almost embarrassingly simple. A determinant changes sign when you swap any 2 of its rows. An electronic wave function has to change sign when you swap any 2 electrons. So write the orbitals across the top, the electrons down the side, take the determinant, and the anti-symmetry is automatic.
So the factorial is the price of the automation. A determinant with n rows has n factorial terms, and n factorial is worse than exponential.
Much worse. And yet the size is not the deepest problem. 2 others forced the change of language. The first you put your finger on in the first minute. The labels carry no information. Nothing you can ever measure depends on them. A notation whose main content is unmeasurable is a notation that will generate work with no physics in it. The second is worse. In that notation, the number of particles is part of the address system. The wave function of 3 electrons and the wave function of 4 live in different spaces, so you cannot write an operator that turns one into the other. There is nowhere for it to point.
Why would I want to? An electron is not going to vanish.
A photon will. That is exactly the problem Dirac was staring at, and it is where all of this comes from. An excited atom emits light. Before, there were no photons. After, there is one. If the number of particles is baked into the structure of your wave function, you cannot write down the process everybody had been measuring since Kirchhoff. Dirac's paper is 1927, Proceedings of the Royal Society, the quantum theory of the emission and absorption of radiation. And out of it come the 2 objects this whole hour is about, plus the first derivation of spontaneous emission from first principles, plus the golden rule of perturbation theory. Not a bad afternoon.
And for us, in a solid, the number of electrons really is fixed. So I want to know whether I need this for a genuine reason or for elegance.
A genuine reason, and here it is. You will not fix the number of electrons, you will fix the number of excitations, and that number changes constantly, because that is what heating something up means. But before any of that, let us kill the labels, because everything follows from that one act.
Then kill them, and start me somewhere I can check the work. Go back to my helium atom. What am I actually allowed to write down?
You tell me, and be strict about it. Not what your notation says about that atom, what you know about it.
I know that there is an electron in this orbital and an electron in that orbital. That is genuinely everything I have. I cannot say which is which, and no measurement will ever tell me, so the question does not have an answer.
Then write down what you know and nothing else. Not, this electron is here and that one is there. Write, this orbital, occupied. That orbital, occupied. Every other orbital, empty. That list, a number for each single particle state, saying how many particles sit in it, is a complete specification. It contains everything the determinant contained and nothing it contained falsely.
Let me make sure I have the picture because it is deceptively plain. I first choose a set of single particle states, orbitals or Bloch waves, or sites on a lattice, whatever basis I like. Then a many-body state is just a long row of boxes, one box per single particle state, with a number written in each box. And the whole content of the state is the row of numbers.
A row of boxes, each with a little light on it. For fermions, each light is off or on, 0 or 1, because the light is a count, and Pauli says you cannot have two. So a many-electron state is a row of lights, some on, most off. And the space of all such rows has a name, after Vladimir Fock, who set it up properly in 1932. Fock space. His title translates as Configuration Space and Second Quantization. And second quantization is a dreadful name. Nothing gets quantized a second time. It is a leftover from Dirac's derivation, where he took a wave function and treated it as a classical field with its own operators.
Bad name, but I want to test the claim that nothing was lost. In the determinant, the minus signs were doing real work. That is where all the exchange physics lived. If I throw away the labels, where did the minus signs go?
Into the order of the boxes, and we spend the next stretch on precisely that. Hold the objection. It is the right one. For now, notice the arithmetic. If I have some number of available single particle states, and each one is either empty or full, then the number of distinct rows is 2 multiplied by itself once per state, which is the same wall we walked into last time, and I am not walking into it twice. But look what changed. It is now a set of yes or no answers, not an unimaginable sum of permuted products. The size did not shrink. The bookkeeping went away.
And is the counting basis special or one among many?
One among many, and it matters. Choose orbitals localized on atoms, and you get one set of boxes. Choose waves running through the crystal, and you get another. Same physics, wildly different bookkeeping, and a state that is one tidy row of lights in one basis is a horrible superposition of 100,000 rows in another. Choosing the right boxes for the problem in front of you is most of the craft in this subject.
Then start me at the bottom. What is the state where every light is off?
The vacuum. And I want you to resist the word nothing, because it is not nothing. It is a specific, perfectly ordinary quantum state, a vector with length 1 sitting in the space alongside all the others. It is the state of the system when there are no particles in it. You can compute its energy. In a serious field theory, the vacuum is a busy, complicated object. In ours, it is just the empty lattice. But it is a state, not an absence.
And I take it every other state is going to be built from it.
Every single one. That is the architecture. One distinguished state, the vacuum, and one operation. Put a particle into that state there, and everything in the theory is generated by applying that operation to the vacuum some number of times. Helium's ground state is start from nothing, add an electron to this orbital, add an electron to that orbital, stop. A lump of copper is start from nothing, do it 10 to the 23 times.
That is a strange inversion. In the way I learned quantum mechanics, the particles were the primary things, and the states were where you put them. You have flipped it. The states are now the fixed furniture, and the particles are counts sitting in them.
That is exactly the flip, and it is why the language survives contact with 10 to the 23. The furniture does not grow. One box per single particle state, whether you have one electron or a mole of them, which is precisely what Dirac needed for photons. Emission is now sayable. It is, the count in this box went up by 1.
Then give me the operator, and give it to me as a verb. I want to know what it does, not what it is.
A verb is exactly right. There are two, and each is defined completely by what it does to a row of lights. Take the first one. Point it at a particular box. If that box is empty, it fills it. You hand it a state with the light off, and it hands you back the same state with the light on. That is the creation operator. And now the interesting half. If the box is already full, it does not refuse politely, and it does not leave the state alone. It gives you 0.
0 meaning what exactly? Because 0 in quantum mechanics is a word people use loosely, and I want the sharp version.
The sharp version is not a state at all. The null vector, length 0. This is not a system with nothing in it. That is the vacuum, a fine, healthy, unit-length state. This is the arithmetic saying, the process you just described has no amplitude. Delete this term. When a 0 comes out of one of these operators, the translation is always, that is forbidden, and everything multiplied by it dies.
Good. So creation switches a light on, and evaporates the whole term if it was already on. And the second operator undoes it.
The second is the annihilation operator, the exact mirror. Point it at a box. If the light is on, it switches it off. If the light is already off, you get 0 again. You cannot take out what is not there. And notice the vacuum now has a definition with no arithmetic in it. The vacuum is the state that every annihilation operator kills. It is the state with nothing left to remove.
Let me try building something. If I want the state with one electron in a particular orbital, I take the vacuum and hit it with one creation operator. If I want 2 electrons in 2 different orbitals, I hit it with 2 creation operators, one for each. And that single expression is standing in for a whole Slater determinant.
For the whole determinant, signs and all. 2 symbols acting on the vacuum replace a 2 by 2 determinant. 20 symbols acting on the vacuum replace a determinant with 2.4 billion terms in it. Not because anything was approximated, because the determinant was mostly bookkeeping, and the bookkeeping is now inside the operators.
And presumably, I can also ask a question rather than do a thing. I want a meter that reads a box without changing it.
You have already got one, and you build it in the obvious way. Take a particle out of the box, then put it straight back. If the box was empty, the first step gives 0, and the whole thing gives 0. If the box was full, you take it out, put it back, and you are exactly where you started. So this combination hands back the same state, multiplied by 0 if empty and 1 if full. It reads the count and leaves the state untouched. It is the number operator, and it is how you say, how many electrons are here, as a piece of algebra, rather than as a question you step outside the theory to ask.
And for the whole system, I add up the meters over every box and get the total particle number.
Add up all the meters, and you have an operator whose value is the total number of particles, which, hold this, is now a dynamical quantity, something the theory computes, rather than a label stamped on the wave function from outside. If it happens to be conserved, that is a theorem you prove about your Hamiltonian, not an assumption you built into your notation. For electrons in a solid, it is conserved. For photons in a laser cavity, it is emphatically not.
Now I want the minus signs back. You promised they went into the order of the boxes, and I have been suspicious ever since, because so far nothing you have said knows anything about fermions.
Nothing I have said knows anything about fermions, and you are right to hold me to it. So far this machinery would describe billiard balls. Here is where the physics enters, and it enters in exactly one line. Build a two-particle state two ways. First, put an electron in orbital A, then in orbital B. Now do it the other way round. B first, then A. Same two orbitals, same two electrons. Physically the same state.
And the anti-symmetry says same state up to a minus sign.
Same state, opposite sign. So we impose it. Swapping the order of two creation operators flips the sign of the whole expression. That is not derived from anything I have told you. It is the definition of what fermion means, transplanted from the determinant into the algebra. Stated in the standard way, do the two operations in both orders and add the two results, and you get 0. Adding the two orderings rather than subtracting them is what anti-commute means, and it is the whole difference between fermions and bosons. Jordan and Wigner wrote it down in 1928 in the Zeitschrift für Physik in a paper called On the Pauli exclusion principle.
Hold on, let me play with that before you go on, because I think something falls out and I want to be the one to trip over it. You said, swap two creation operators, flip the sign. That is a statement about two different boxes. What happens if I aim both of them at the same box?
Do it. Follow the rule and see what it says.
The rule does not care that they are the same. Swap them, flip the sign, but swapping two identical things leaves the expression looking exactly as it did. So I have an object which, when I rearrange it into precisely itself, has to come out as minus itself. And the only number equal to minus itself is 0. So creating two electrons in the same state does not give a small amplitude or a suppressed amplitude. It gives nothing at all.
And you have just derived the Pauli exclusion principle. Not stated it, not assumed it, derived it in about 15 seconds out of a sign convention. That is the moment this language earns its keep. In the way you first met it, exclusion is a rule handed down from outside. Thou shalt not put two electrons in the same state. Here it is arithmetic. The operator that would do it squares to 0. There is no state to forbid, because the expression that would name it is not a state.
Which also explains why my lights only go off or on, rather than counting up to 7. That was not a separate assumption. It is the same fact.
It is the same fact wearing a different hat, and that is the mark of a good language. Things you had to remember separately collapse into one thing. And notice what this buys physically. Every consequence of exclusion, the shell structure of atoms, the entire periodic table, the fact that a chair holds your weight instead of collapsing, the pressure that stops a white dwarf star from imploding, and the Fermi sea we will spend the rest of the hour on, all of it descends from one sign in one algebraic identity.
Then let me put it in one sentence so I cannot wriggle out of it later. Exclusion is not a law about electrons that somebody discovered and bolted onto quantum mechanics. It is what indistinguishability looks like once you stop pretending the electrons have names.
And having stopped pretending, you get the opposite case for nothing, which is the tell that this was the right move. What if the swap costs a plus sign instead of a minus?
Then my derivation collapses. Swapping two identical creation operators would give back the same expression with the same sign, which is no constraint at all, so the box can hold as many as it likes.
Which is exactly what happens. You get bosons, and the counts run 0, 1, 2, 3, upwards without limit. And it is better than merely permitted. Aim a boson creation operator at a box that already holds some particles, and the amplitude it hands back is bigger than if the box had been empty. It grows with the number already in there. I am skipping where that growth comes from. It falls out of the same relation in 2 lines, and what it would show you is that the enhancement goes as the square root of 1 more than the count already present.
Then say what that does, because an amplitude that grows with occupancy is not a technicality. It means bosons prefer to go where bosons already are, not as a metaphor, as a number. A photon is more likely to be emitted into a mode that already has photons in it, which is stimulated emission, which is a laser. And a cold gas of bosons should pile into one state rather than spread out.
All of it, and the pile-up is Bose-Einstein condensation, and when we get to helium, it is superfluidity. Two sign conventions, two kinds of matter, and every other line of the construction identical.
Then tell me how much of the minus sign is derived and how much you simply asserted because you slipped it in as a definition.
Asserted. I told you the swap costs a minus sign. I did not show you it must. What underwrites it is the spin statistics theorem, which is genuinely a theorem and genuinely relativistic. It comes from demanding a consistent quantum field theory with a lower bound on its energy. I am skipping it. What it would show you is that half-integer spin forces the minus sign and integer spin the plus, with no third option. And one exception to flag because we need it later. The argument that the swap can only cost plus or minus 1 relies on living in 3 dimensions. In 2 dimensions, particle paths can wind around one another in a way they cannot in 3, and other phases become possible. Those are anyons, and they turn up in one of the strangest measured facts in the subject.
Then let me ask the question that decides whether any of this was worth it. I have a language for states. What does a Hamiltonian look like in it?
Like a list of sentences, every one with the same grammar. Take a particle out of this state, put one into that state with this amplitude. That is all any term ever says. An electron hopping to the next atom, remove it here, create it there. An atom absorbing a photon. Destroy a photon, promote an electron from its ground orbital to its excited one. 2 electrons scattering. Remove 2 from wherever they were, create 2 where they went, weighted by how strongly they push.
So terms come in sizes, and the size is the number of particles involved.
Exactly, and it is the most useful classification in the subject. One-body terms, one annihilation, one creation, are anything acting on each particle separately. Kinetic energy, an external potential, the periodic potential of a lattice. Two-body terms, 2 out, 2 in, are interactions, one pair at a time. Coulomb repulsion is two-body, and essentially everything hard in this series is downstream of that fact.
And here is the thing I notice, which is either trivial or the whole point. Nothing in that Hamiltonian mentions how many particles there are.
That is the whole point, and it is worth saying slowly because it is easy to nod past. The Hamiltonian for 1 electron in a crystal and the Hamiltonian for 10 to the 23 electrons in the same crystal are the same operator, character for character. What differs is the state you apply it to. In the old notation, you rewrote the Hamiltonian every time the particle number changed, because its shape depended on how many coordinates there were. Here the operator is fixed furniture, and the particle number lives in the state.
Which is presumably also why one-body problems are easy and two-body terms are not.
It is exactly why. If every term removes one particle and creates one particle, the operator never correlates 2 particles with each other. You solve the single particle problem, a small matrix, 1 row per box, and then build every many-body eigenstate by filling those states up. That is the entire content of band theory. A one-body problem, solved once, then occupied. The moment a term takes out 2 and puts back 2, that factorization is dead. What one electron does depends on what another is doing, and there is no set of single particle states you can fill to get the answer.
So the language has not made the problem easier.
The language has made the problem sayable, which is a smaller claim than people sometimes make for it. It has not solved anything. It lets you write a Hamiltonian for 10 to the 23 interacting particles on one line and talk about processes instead of coordinates, which is enough to build the model that has occupied this field for 60 years. And I want to build it with you now, one term at a time, because both terms are things you can already write.
Then set the stage. What is the system?
The crudest crystal you can imagine, and still call it a crystal. A regular array of sites, each one an atom with a single orbital available. Electrons live on those sites, so each site has 4 possibilities: empty, 1 electron with spin up, 1 with spin down, or 2 with opposite spins. And that is the entire stage. No core electrons, no orbital shapes, no lattice vibrations, no long-range fields. Almost everything real has been thrown away.
That is a lot of throwing away. Defend it now rather than later, because otherwise I will not believe anything that comes out.
Fair. We are not modeling a material, we are asking whether one specific competition produces the phenomena we care about. Electrons wanting to spread out against electrons, not wanting to be near each other. Everything I discarded is inessential to that. If the competition alone generates magnetism and insulators where band theory says metal and possibly superconductivity, then those phenomena belong to the competition and not to the chemistry of any particular compound. If it fails, we learn that too, which is why it is worth an hour on a Hamiltonian that describes no substance on the periodic table.
A placement. Then term 1. What is the simplest thing an electron can do on a lattice?
Move next door. And you can write it now, in the grammar we just built. Destroy an electron on this site, create one on the neighboring site, with some amplitude. Sum that over every neighboring pair in the crystal and over both spins, and you have the first half of the model.
And that amplitude is not a new quantity, is it? That is the tunneling amplitude. The nitrogen leaking through the triangle of hydrogens, and the electron leaking between 2 atoms to make bonding and antibonding. Same number.
The same physical quantity in its third costume, and I want that recognized because it is the spine that runs through this entire series. It is the amplitude for a particle to be found on the other side of a barrier it has no classical right to cross. In a molecule, it splits 2 levels. In a crystal, it turns levels into bands. Here it is written as a verb: remove there, create here, and physicists call it T for transfer. Everything else about the lattice is in how many neighbors each site has.
2 things I want to nail down. First, does it have to go both ways?
It has to, and not for reasons of taste. Allow the hop left to right, and not right to left, and your Hamiltonian is not Hermitian. Its eigenvalues go complex, and probability leaks out of the system. So the term always comes as a matched pair. Hop that way, hop back, one number governing both.
Second, the spin. Does the electron keep it while hopping?
In the plane model, yes. The electron arrives with the spin it left with. That is an assumption, and a consequential one. Break it, let the hop rotate the spin, which is what spin-orbit coupling does. And you get a completely different world, with edge states that conduct while the bulk insulates. A long way down the road.
Then let me try to guess what this term alone gives me, since it is a one-body term and you told me those are easy. It is the tight binding model, so I get a band. And I would guess the band's width depends on how many neighbors each site has, because each neighbor is another escape route.
Guess the scaling and you will have it exactly. The width comes out as twice the hopping times the number of nearest neighbors. On a square lattice in the plane, 4 neighbors, so 8 times the hopping from the bottom of the band to the top. And that is not a fluke of that one lattice. A chain gives 4 times the hopping, a cube gives 12. It is not a universal law across every lattice you could draw, but the instinct is right everywhere. More neighbors, more ways out, wider band. Solid, uninteresting, and exactly solvable, no matter how many electrons you put in, because with only this term, the electrons never notice one another.
Give me the number for something real, so I know what scale we are on.
In the copper oxide planes of the high-temperature superconductors, The effective hopping in the one-band description is around 4/10 of an electron volt, which puts the bandwidth at something like 3 electron volts. An ordinary number for a narrow band in a transition metal compound, and the number to hold, because in a moment we compare something to it.
Then the interaction. And I want the unapproximated version before the simplified one, because the Coulomb force does not stop at the nearest neighbor.
The unapproximated version is a disaster, and you should see it. Coulomb repulsion falls off as 1 over the distance, which in a crystal means every site talks to every other. Every pair, at every separation, with an amplitude that never quite dies. In our grammar, take 2 electrons out of any 2 sites, put 2 back into any 2 sites, for every choice. The number of terms grows like the 4th power of the number of sites, and none is obviously negligible.
Then something has to save us, and I do not think it is a mathematical trick.
It is not. It is physics, and it is one of the most important facts about a metal. The bare Coulomb tail is not what 1 electron feels. The moment you put an extra charge into a sea of mobile electrons, the sea rearranges. Like charges are pushed away, so a deficit of negative charge builds up around your electron, and from a distance the two nearly cancel. The interaction stops falling off as 1 over the distance and starts falling off exponentially, and the length over which it dies is shorter than the spacing between the electrons themselves, about half an angstrom in copper, against an electron spacing of a couple of angstroms. That is screening, and it means the long tail we were panicking about is mostly not there.
So the interaction is short-ranged, and I keep the shortest-ranged piece of all. 2 electrons on the same site.
The same site. The one case screening cannot rescue, because there is no room for the C to get between them. 2 electrons in the same orbital on the same atom are as close as electrons in a solid ever get, and they pay for it. So keep the on-site term and throw the rest away. I want to flag that as the drastic step it is, because most of what is questionable about this model is right here. Neighboring site repulsion is not 0. Where it matters, people put it back and the physics changes.
Now let me write the term, because I think I can. It has to charge an energy when, and only when, a site has 2 electrons on it, and I have a meter that reads occupancy. So, the meter for spin up on that site multiplied by the meter for spin down on that site multiplied by an energy.
That is precisely it, and look at the switch you have built. Each meter reads 0 or 1, so the product is 0 unless both are 1. The term is silent, completely, exactly silent, for an empty site and for a site holding a single electron of either spin. It speaks only when a site holds both an up and a down electron, and then it charges a flat fee. Physicists call that fee U, the on-site repulsion.
And notice what is doing the work in the background. The term never needs to consider 2 electrons of the same spin on a site, because that state does not exist. The algebra already deleted it.
The algebra already deleted it, which is the anti-commutator paying its first physical dividend within 5 minutes of being derived. Pauli is not an extra clause in this Hamiltonian. It is a property of the symbols.
Then tell me what that energy is, physically, not the letter, the process I could in principle measure.
Take 2 neutral atoms, far apart, each with 1 electron. Move 1 electron from one atom to the other. Now you have a positive ion and a negative ion, and the energy you paid is the cost of taking the electron off minus what you got back for putting it on. Ionization energy minus electron affinity. For hydrogen, that is 13.6 electron volts of ionization, less about 3/4 of an electron volt of affinity, so call it just under 13 electron volts. That is the bare on-site repulsion for a hydrogen atom, and it is enormous.
But in a solid, it must be smaller, or nothing would ever conduct.
Much smaller, for the reason we just discussed. The rest of the crystal screens it. In the effective single-band description of the copper oxide planes, the useful value is around 3 electron volts. And now do the comparison I set you up for.
3 electron volts of repulsion against a bandwidth of about 3 electron volts. They are the same size. Which is exactly the scandal you left me with last time, in different clothes. What I want to ignore is as big as what I want to keep, and there is no small parameter to expand in.
There is no small parameter, and now you have assembled the entire model. Say it back as 2 sentences of English, with no symbols in either.
1. Electrons hop between neighboring sites with an amplitude that sets how much they would like to spread out. 2. Any site holding 2 electrons pays a fixed energy penalty. That is the whole thing.
That is the whole thing, and it has a name, the Hubbard model. John Hubbard, 1963, Proceedings of the Royal Society, Electron Correlations in Narrow Energy Bands. And it was in the air. Martin Gutzwiller and Junjiro Kanamori published essentially the same model the same year, from different directions, all 3 of them chasing the magnetism of the transition metals. Hubbard's own question was why the standard theory of bands could not account for what iron, cobalt and nickel actually do.
And I should say what strikes me about the 2 terms, which is that they are written in different languages. The hopping term is about where an electron is going. The interaction term is about where electrons are. Those are not the same kind of statement.
They are not, and that observation is the entire difficulty of the subject, so let me make it sharp. The hopping term is simple in a basis of waves running through the whole crystal. In that basis, it is diagonal. It is just a band. It is done. The interaction term is simple in a basis of electrons sitting on definite sites. In that basis, it is diagonal. It is just a phi per doubly occupied site. It is done. Each term alone is trivial. There is no basis in which both are simple. They do not commute.
So the difficulty is not that either term is complicated. It is that they disagree about what an electron is.
That is the cleanest statement of the many-body problem I know, and it is worth carrying for the rest of this series. Neither term wins outright, and the physics lives in the standoff, which means an enormous amount depends on a single dimensionless number, the on-site penalty divided by the hopping. Change both by the same factor, and you have merely changed your units.
An enormous amount, but not everything, and I want to catch you before you move on. That ratio says nothing whatsoever about how many electrons are in the crystal. Put 1 on every site, and the phi bites on every attempted move, because there is nowhere to go that is not already occupied. Put 1 on every other site at exactly the same ratio, and half the lattice is empty, and an electron can wander for a long time without meeting anybody. That is a second knob, and I would expect it to change everything.
It changes everything, and I would rather you made that correction than me. 2 axes, not 1. The penalty over the hopping and the number of electrons per site, the filling. And the filling is no junior partner. The hardest region in the subject is the one you reach by taking a state you understand at 1 electron per site and removing a few % of the electrons. That is what doping a material means, and the argument at the end of this series happens entirely inside it.
Then hold the filling at 1 electron per site and walk me along the ratio, and we can come back. What happens at the 2 ends?
At one end, no penalty at all. Pure hopping, free electrons in a band, a metal, the whole single particle picture, exactly solvable for any number of electrons. At the other end, no hopping. The atomic limit, every electron nailed to its site. The energy then does not depend at all on which way the spins point, so the ground state is fantastically degenerate. Every arrangement of up and down is equally good. Also exactly solvable, and also completely inert.
And in between, both terms are on, and it is unsolved.
In between it is unsolved, in the dimension we care about. In one dimension, Elliott Lieb and Fa-Yue Wu solved it exactly in 1968 using a technique of Hans Bether's that works on a line and almost nowhere else. And they found that with 1 electron per site, any repulsion at all, however small, opens a gap. There is no threshold. In 2 dimensions, after 6 decades of serious effort, we do not have the answer. The best numerical work finds stripes, the electrons arranging themselves into alternating rows of charge and spin, competing with superconductivity so closely that which one wins turns on details you would have thought were cosmetic. A study in Science in 2024 found superconductivity coexisting with stripes once a second. Longer hop is allowed. It is genuinely open, and I would not leave you thinking it is nearly closed.
2 terms, 60 years, and before you tell me why, let me check the brute force route really is shut. Because we said each site has 4 possibilities, and I can multiply 4 to the power of the number of sites. So 20 sites is already of order 1 trillion rows, which is exactly the ceiling you quoted me last time, and now I can see where the ceiling comes from, rather than being told it.
That is the wall in this model's own currency, and the usual way round it is shut too. When enumerating is hopeless, you stop enumerating and start sampling. And for bosons that works superbly. For electrons it fails, for a reason you will recognize. The quantity you would like to treat as a probability is not positive. It changes sign from one configuration to the next. The cancellations grow with the size of the system, and your error swamps the answer. So there is no brute force and no clean sampling, which is why people have started building the model out of atoms instead. Take a gas of fermionic atoms, cool it to a few billionths of a Kelvin, and trap it in a lattice of standing wave laser light. The atoms hop between wells and repel when they share one, and you have a Hubbard model made of things that are not electrons. In 2017, a group at Harvard cooled such a lattice far enough to watch antiferromagnetic order form, and the correlations reach right across the sample. That is a laboratory computing a Hamiltonian nobody can solve. What it can and cannot settle is a conversation for the end of this series.
Before we leave the model, I want one thing that comes out of it. Something that neither term contains on its own, so that I can see the 2 of them producing physics, rather than just sitting next to each other.
Then take strong repulsion and 1 electron per site. The penalty is large, so double occupancy is essentially forbidden, and every site holds exactly 1 electron. Nothing can move. To move, an electron would have to land on a site that is already occupied, and it cannot afford to. So the system is an insulator. Not because a band is full, the band is exactly half full, and every word of single particle theory says metal. It is an insulator because of the phi. Now ask the question that matters. What are the spins doing?
Nothing, by what you said a minute ago. In the atomic limit, all the spin arrangements had the same energy.
In the atomic limit. But the hopping is small, not 0, and small is very different from 0 when something is degenerate. Consider 2 neighboring sites, each with 1 electron. Suppose their spins are parallel, both up. Can either one make a brief excursion onto its neighbor and come back?
No, it would have to arrive at a site already holding an up electron, and that state does not exist. The creation operator gives 0. So parallel spins are frozen, and they get nothing.
Now make the spins anti-parallel.
Then the visit is allowed. Expensive, because it makes a doubly occupied site, but it is a virtual excursion, so it does not have to conserve energy while it happens, only to end where it can. Out and back. And second-order perturbation theory always pushes the ground state down. Mixing in anything above you can only lower you. So the anti-parallel arrangement has an escape route that the parallel one does not, and it therefore has lower energy.
You have just derived anti-ferromagnetism, and I want to name what happened. Nothing in the Hubbard-Hamiltonian couples one spin to another. The spins are in there. The hopping carries a spin label. The phi is charged to an up and a down, but no term ties the direction of one electron's spin to the direction of any others. There is no magnetic term anywhere in it. No field, no dipole-dipole coupling, nothing that knows what a magnet is. We wrote a rule about hopping and a rule about crowding, and out of it comes a force that aligns neighboring spins opposite to each other. It is called superexchange. Philip Anderson worked it out properly in the 1950s. And before I give you its size, guess it. How should it depend on the hopping and on the penalty?
Hopping squared, because the electron has to go out and come back. 2 hops, and each one costs an amplitude. And divided by the penalty, because the penalty is what it costs while it is over there. Bigger fee, shorter visit, weaker effect.
That is the entire structure of the answer, and you got it from the picture rather than the algebra. The coefficient out front is 4. Put in 4/10 of an electron volt of hopping and 3 of penalty, and you get a couple of tenths of an electron volt. The measured value in the parent compound of the copper oxide superconductors, from scattering neutrons off it and watching the spin waves, is about 130 thousandths of an electron volt, so the one-band mapping overshoots by roughly a factor of 2. A bracket, not a bullseye. But express the measured number as a temperature, and it is around 1500 Kelvin, above the Curie temperature of iron.
So the magnetism in those materials is not some feeble relativistic effect. It is the Coulomb repulsion and the Pauli principle working together, wearing a disguise.
Electrostatics and a minus sign. There is no magnetic force in the story at all. And that is what I mean by the language earning its keep. 2 terms, neither of which mentions magnetism, produce a magnetic interaction with an energy scale you can measure with a neutron beam.
Then let me come back to something you said early on and never cached. You said I would not be fixing the number of electrons, I would be fixing the number of excitations. I want that now because it sounds like the thing that makes any of this tractable.
It is the thing. Our vacuum, every light off, is the wrong place to start for a metal. A metal in its ground state is not empty. It is a Fermi sea, 10 to the 23 electrons, filling every state up to the shoreline. And almost all of that sea does nothing. An electron deep below the surface cannot absorb a small amount of energy because every state it might move to is occupied. It cannot scatter, it cannot respond to a field, it cannot be seen by any low-energy probe. It is inert.
So the honest count of what is going on in a copper wire is not 10 to the 23.
It is the thin shell near the shoreline and nothing else. The fraction we put a number on last time. So we change the accounting. We declare the filled sea to be the new vacuum. Not nothing again, but a very rich, very heavy nothing. The reference state from which we count. Then we ask what the operators mean relative to it.
Above the shoreline, unchanged. Those boxes are empty, so creating an electron there adds a genuine excitation.
And below the shoreline, everything inverts. Those boxes are full, so creating there gives 0. Nothing to do. What does something is annihilation. Remove an electron from deep in the sea, and you have made an excitation, a missing electron, an empty box where the ground state has a full one. That is a hole, and a hole is not a bookkeeping convenience. It has an energy, it has a momentum, it moves, and its charge is positive, because the ground state was neutral and you took a negative charge out.
So relative to the new vacuum, the annihilation operator for a deep state has become a creation operator for a hole.
Exactly that swap, and once you make it, both kinds of excitation are created rather than removed, and the ground state is once again the thing that everything annihilates. Only the definition of nothing moved. And the payoff is the whole reason many body physics exists. At room temperature, there are very few excitations in that sea. You have replaced 10 to the 23 strongly interacting objects with a dilute gas of particles and holes. Dilute problems we can do, dense ones we cannot.
I want to check that holes are physical and not a story we tell. What do I measure?
Run a current through a metal foil in a magnetic field and measure the sideways voltage, the Hall effect. Its sign tells you the sign of the charge carrying the current. In sodium, it is negative, as you would expect. In beryllium, it is positive, and in aluminium too, once the field is strong enough. Those metals conduct as though the carriers were positively charged, and they are. The relevant band is nearly full, and it is the missing electrons that move. Rudolf Peierls worked that out in 1929 at Heisenberg's suggestion, and Heisenberg made the whole a general concept in 1931. And every p-type transistor ever fabricated works by moving holes about deliberately.
And I have a suspicion about where this idea came from originally, because it is too good not to have been used somewhere more famous.
It was Dirac's one level down. His equation for the electron had solutions with negative energy, which is a catastrophe. Every electron in the universe should cascade downwards forever. His answer, in 1930 in the Proceedings of the Royal Society, was that they do not cascade because those states are already occupied. A filled sea, infinitely deep, unobservable because it is uniform. A hole in it would be a particle with positive charge and positive energy. He first hoped it was the proton. By 1931, he accepted it had to have the electron's mass and be something new. Carl Anderson found it in a cloud chamber in 1932 and had the Nobel Prize 4 years later.
So the positron and the hole in a semiconductor are the same idea.
The same idea, and the deepest instance of the rule this whole hour has been building towards. What propagates, what carries energy and charge and momentum, what your instruments detect, is not the constituents. It is the disturbances of whatever the system does when left alone. Nobody measures the Fermi sea. Everybody measures its ripples.
Then I want the thing you have been circling since last time, and I want it stated as a claim so that I can refuse to believe it.
Here is the claim, as precisely as I can put it. Take a metal with strong repulsion between its electrons. Consider its low-energy excitations, the ones just above the ground state, near the shoreline. The claim is that they are in one-to-one correspondence with the excitations of a gas of electrons that do not interact at all. Same charge, same spin, same labeling by momentum, same counting. What differs is a short list of numbers. The thing behaves as though it were heavier than a bare electron. It has a finite lifetime rather than living forever, and it carries only a fraction of the weight a bare electron would. But structurally, the strongly interacting system's excitations look like a free gas. That object is the quasi-particle.
And you told me what it is made of last time, an electron dragging the cloud of charge it has pushed out of its way. So a heavier object, because it has to drag the cloud along.
That is the picture, and the picture is not the argument. So let me be exact about what has and has not been established, because this is the point at which people quietly stop following. Nothing I have said today implies any of it. The language I just built is completely indifferent to how strong the interaction is. It would let me write down a Hamiltonian in which the excitations are nothing like electrons at all, and such Hamiltonians exist and are realized in real materials. The claim is an additional physical hypothesis about a particular regime, and it is Lev Landau's from 1957.
Then let me push, because I think you have conceded more than you meant to. If the formalism is indifferent, the formalism has brought me nothing physical. It has only brought me the ability to state a question tidily.
That is exactly what it has brought, and I would not claim more. A language does not contain physics. It makes certain questions askable that were previously not even formulable. And, are the low-lying excitations of this interacting system in one-to-one correspondence with those of a free one, is a sentence you cannot say without the machinery of this hour. You would have no word for excitation independent of particle.
Then tell me what would have to be true for it to hold, and I will tell you whether I believe it.
3 things, on the record, so that next time is a settling of debts rather than an assertion. First, the correspondence has to survive turning the interaction on. The states must map across with none appearing or disappearing. Second, the quasi-particle has to live long enough to deserve the name. An excitation with a lifetime shorter than one oscillation is not a particle in any useful sense. It is a smear. Third, the whole thing is restricted to low energies near the shoreline, and we have to say how near.
The lifetime one, I think I can attack now, actually, and I want to try because we have just spent an hour on exclusion. Take an electron sitting a little above the Fermi surface. To decay, it has to scatter off something, another electron in the sea. But the partner has to come from below the surface and end up above it. And my electron has to end up somewhere above it too. Both final states have to be empty. And as I move my electron down towards the shoreline, the range of energies available for all of that shrinks. So the number of ways to scatter shrinks. 2 independent squeezes. So I would guess the rate dies like the excitation energy squared.
That is the right instinct and the right answer, and I am not letting you bank it today because the argument needs the phase space counted rather than waved at, and the conclusion drawn, which is the striking part. The closer to the shoreline, the longer lived the excitation, so quasi-particles become better defined exactly where we need them. Pauli protects them.
Which is the same minus sign again.
The same minus sign for the 5th time today. It stopped 2 electrons occupying one box. It made the sea inert. It forced anti-ferromagnetism out of a Hamiltonian with no magnetism in it. It is the reason the sampling that works beautifully for bosons collapses for electrons, because the sign that flips under a swap is the very sign that ruins the average, which is why nobody can simply compute their way to the answer and why people are cooling atoms instead. And now it is what keeps a quasi-particle alive long enough to be called one. And one caveat before we stop. That whole structure is a hypothesis with an enormous amount of evidence behind it, not a theorem. There are materials in which it demonstrably fails, where the resistivity does the wrong thing over an enormous range of temperature, and the excitations near the shoreline are not particles of any kind. We will get there, and there is no accepted explanation waiting for us when we do.
Then, before we stop, let me pay the bill on what I walked in here without. 3 things, and if I cannot say them cleanly, I have not got them. First, a creation operator is a verb. It switches a box on. Aim it at a box that is already on and you get 0. Not a small amplitude, nothing. The term dies. And the reason is one sign convention. Swapping 2 of them flips the sign of the expression. So aiming 2 at the same box makes the expression equal to minus itself. And the only thing equal to minus itself is 0. Pauli exclusion is not a rule imposed on the theory. It is arithmetic.
And flip that one convention, and you get bosons piling into a single state instead, which is a laser and a superfluid. The whole of matter sorted by a sign.
Second, I count occupations instead of tracking labelled particles because the labels were never real, and carrying them costs me factorially many terms, whose only job is to cancel each other. Counting throws away nothing measurable. It also takes the particle number out of the notation and puts it into the state. So one Hamiltonian serves for any number of particles, and processes that change the number become sayable.
And the price, which I would rather you carried than discovered later, this is a change of language, not a solution. Every hard problem is still hard. What changed is that you can write it down in one line and argue about it.
And third, The thing I am not allowed to believe yet. A quasiparticle is claimed to be a low-energy excitation of an interacting electron liquid that is in one-to-one correspondence with the excitation of a free gas. Same charge, same spin, same momentum label, but heavier, shorter-lived, and carrying less weight. An electron plus the disturbance it drags along, and nothing today justifies it. The formalism is indifferent to interaction strength. The interaction is not small, and neither the correspondence nor the lifetime has been established. It is Landau's hypothesis, not a consequence of anything we built.
That is precisely the state of the account, and it is the debt for next time. Because the question underneath it is genuinely absurd when you say it out loud. Every electron in a copper wire is being shoved by every other electron with an energy comparable to its own, and the wire behaves as though they were a gas of nearly free particles that happen to be a bit heavy. That is not a small discrepancy to be tidied up. It is the difference between a soup and a gas, and something has to explain why the soup is entitled to pass for one. Next time we find out why, we meet the man who worked it out with almost no calculation, and we look at the photo emission experiments where you can watch the quasi-particle peak sharpen as you approach the shoreline.
So the language is built and the bill is outstanding.
The language is built. Bring the sea, and we will find out what protects the ripples.